Welcome back. In this lecture, we will just touch upon an, a very important topic. We cannot really do justice to this topic in this brief lecture. The issue we will be introducing is the electrochemomechanical coupling in the context of fuel cells and batteries. This is of a lot of contemporary interest. In the next few years, a lot of important issues will be dealt with, especially in the context of solid state batteries. Often, an axial load is applied in the context of fuel cells and batteries. A way to think about its utility is via this schematic. Supposing you have an interface between two electrochemical components. This can be an electrolyte, this can be an electrode, and both are made up of solids. It's very hard to have a perfectly smooth solid. Often you have a rough solid interface, and the resistance is inversely proportional to the number of contact points. The more the number of contact points, the lesser will be resistance. And one way to decrease the resistance and increase the contact points is to apply a load in this direction. This is the axial load we are referring to. If you apply a load, it brings together more contact point between this component and this component. An empirical relationship is provided here. The conductance, which is inversely proportional to contact resistance, is proportional to some constant. The amount of axial load you apply, and this is an exponent which has to be obtained experimentally. So some plot in the context of fuel cell is shown here. On the y-axis, we have resistance. On the x-axis, we have a compressive load. So this is for a rough electrode, rough interface, and this is for a relatively smooth interface. Overall, the observation is that as you increase the compressive load, the resistance comes down. That is the central observation. And in addition, you see that a rough interface has greater contact resistance compared to a smoother interface. This is in the context of fuel cell, but in the context of, so we will also look at this issue in the context of solid state battery. Another important aspect in the context of fuel cell is the following. Context of anode supported solid oxide fuel cell. We've addressed what we mean by anode supported and electrolyte supported and cathode supported in a previous lecture. You can refer to this lecture to understand the geometry of this particular type of solid oxide fuel cell. So here, the thickness of the anode is much more than thickness of electrolyte as well as the cathode. So because the solid oxide fuel cell operates at a fairly high temperature, let's say 800 degrees centigrade, when the temperature is raised, the anode expands, and it is the expansion of anode is pretty much unimpeded by the expansion of the electrolyte and other components. Because of this aspect, of that is the unimpeded expansion of anode, pretty much unimpeded expansion of the anode, there will be additional stresses in the electrolyte. So the way to think about this is, supposing we are focused on the electrolyte, sigma refers to the stress in the electrolyte. This refers to the Young's modulus of the electrolyte, Poisson ratio of the electrolyte. What is crucial to understand are these two terms. This is the S refers to support, in this case anode support. I refers to the thermal expansion coefficient of the electrolyte. AS refers to the thermal expansion coefficient of the anode. Because the electrolyte is made up of a different material compared to the anode, they will have differences in thermal expansion coefficient, because of which there will be different levels of expansion of the two components. So T naught refers to a temperature wherein there were no stresses, and T refers to the temperature, especially it may refer to the temperature of operation of the solid oxide fuel cell. The main take home message is that because of differential thermal expansion and because of high temperature of solid oxide fuel cell, uh, stresses are developed in different components of the solid oxide fuel cell. This will have a lot of implications. All these issues you might have seen in an undergraduate course in material science, especially on mechanical properties of materials. You typically start uh, lectures on mechanical properties of material by plotting the stress versus strain relationship in different kinds of materials. The solid oxide fuel cell is typically a ceramic material. It is often brittle. So when there are significant stresses that are developed in a particular component, because they are brittle, they may fracture easily. Brittle materials do not accommodate a lot of plastic deformation. They tend to fracture after a particular stress. So, as opposed to ceramics, metallic components stress strain behavior is shown here. So, there is a particular level of stress and strain where there is a linear dependent of stress in with respect to strain. From when you go to A to B, still there is linear dependence of stress and strain, but the slope is different. The nonlinearity kicks in this region, B and C, but still, if you remove the stress, there is reversible strain in this region. But beyond the point C, C is refers to yield strength, there is permanent plastic deformation of the material. Ductile materials are those that show significant plastic deformation before failure occurs. But in the context of solid oxide fuel cell, this kind of behavior is more relevant. So, managing stresses due to differential thermal expansion and high temperatures is an important practical issue that has to be dealt with in the context of solid oxide fuel cell. There is another aspect in the context of SOFC. To prevent gas leakage, you apply a compressive stress. So this compressive stress is applied via tie rods. So you tighten these tie rods to prevent leakage of gases. But what is important to note is that there is another aspect of mechanical behavior called creep. Creep is the permanent deformation of the material when the material is exposed to stresses for a long period of time. So because the SOFC is operated for a long period of time under uh, compressive stresses, there can be permanent deformation, permanent compression, because the compressive load is enforced for a long period of time. This feature is called creep, and what is known is that the creep deformation is enhanced with increase in temperature. If the temperature is more, the susceptibility of the material to creep is also greater. Therefore, the issues of creep in SOFC is greater because the temperature of operation is fairly high. Whole slew of issues come together in the context of solid state batteries. This is an area of enormous contemporary interest. An excellent review material is available in this manuscript called Solid State Batteries, the Critical Role of Mechanics, wherein the electrochemomechanical coupling is brought out. This was just published, so it's very uh, uh, the latest results are presented in an important context of solid state batteries. One of the frontier research area in lithium ion battery is the solid state uh, battery, uh, wherein instead of having uh, graphite anode, you have a lithium metal as the anode, because this increases the energy density of battery. The cathode is always a solid in all lithium ion batteries, as opposed to liquid electrolytes in the most common lithium ion batteries. The electrolyte in solid state battery is a solid. This brings in mechanical coupling at a very different level. In the solid state electrolyte, there can be issues of fracture because of um, incorporation of or percolation of dendrites. These are structures, pointy structures that emanate out of the lithium anode because of, let's say, fast charging of the batteries. So they may penetrate into the solid state electrolyte and cause fracture of the solid state electrolyte. Other uh, kinds of mechanical effects like stress relaxation, plasticity, and creep also come into play. Fatigue is a mechanical failure due to cyclic load, because intercalation of lithium ions and de-intercalation of lithium ions into the cathode generate cyclical loads. Fatigue is also important in um, cathode failure in the context of solid state batteries, or in general um, lithium ion batteries. Again, other issues like fracture and stress relaxation are also important. We cannot do justice um, to this topic. If you're interested, a good place to start learning about this topic is this manuscript. Please look into this. This is a topic that is worth addressing for over an entire semester course. This is just to introduce you to this important topic. In the next brief lecture, we will look at a case study on fuel cell that is used for space application. Thank you.